with this, now I'd like to introduce the next speaker. So you guys can see the slide, Janzeer.
Yes, Amir.
Yes.
Okay. So our next speaker is Dr. Hyun-Wook Jin. He's going to be giving
Sorry,
a talk.
Amir, I think we're not seeing the slides, but your browser is open. Like the slides are not showing up.
Okay, so just give me.
Yes, and it's in the presentation mode. Maybe you want to switch to full screen mode.
Yes, now it's
yes.
Okay, that's good. Our next speaker is Hyun-Wook Jin. He's a professor in the Department of Computer Science and Engineering at Konkuk University, Seoul, Korea. He's leading the System Software Research Lab at Konkuk University. And before that, he was a research associate in the Department of Computer Science at OSU. And he has a PhD degree from Korea University. His main research focus is on operating systems for high-end computing and cyber physical systems. And he will be giving a talk on kernel-level support for MPI Intra-Node communication post-LiMIC. So he'll be giving a project overview on that. So thank you, Dr. Jin. Please take it away. So I'll stop sharing and you can start sharing your slides.
Okay. Do you see my slide?
Yes, I do. Yes. Please take it away. Thank you.
Shall I start?
Sure, please go ahead.
Hello, everyone. Today, I would like to give an overview of our Post-LiMIC2 project that aims to improve the performance of MPI Intra-Node communication on multi and many core systems. The work I present today has been done with my graduate students in System Software Lab at Konkuk University. I will start my presentation with the background of our project. In this part, I will mostly explain existing implementations of kernel-level support for MPI Intra-Node communication. Then I will go over our Post-LiMIC2 project as shown in this slide. The main issues we want to address are power efficiency, skew tolerance, and better manageability in MPI Intra-Node communication. I will also present our preliminary measurement results on these issues, and I will conclude my talk. As many of you know, the kernel-level support for MPI Intra-Node communication has been suggested to reduce the number of data copies on the communication path. The basic idea of this scheme is to map the buffer of a process, let's say process A, into the address space of another process, let's say process B. This memory mapping can be done by only kernel level operations. Thus, people implemented this scheme at the kernel level. Once the memory mapping is done, the data of process A can be directly moved to the buffer of process B. Most implementations of kernel level support provide this direct data movement between processes, reducing the number of data copies into one. This is shown in the left side figure. Or some other implementation allows process B to read data directly from the source buffer of process A. Thus, this removes data copies. This is shown in the right side figure. The former one is beneficial for point-to-point communication of large messages, while the latter is beneficial for a read-only case. Let me explain a little bit more about well-known implementations of kernel-level support in following slides. LiMIC is the first implementation of kernel-level support for MPI intra-node communication was suggested when I was in Professor Panda's group in 2005. Since it had a problem in tag matching, we redesigned LiMIC and named it LiMIC2. which has been released with MPI-2 from 2009. If you are interested in LiMIC2, you can enable it as shown in this slide. Then another implementation called KNAM was suggested. Compared to LiMIC2, KNAM provided advanced features such as asynchronous communication, enhanced collectives, and security model. I will talk more about asynchronous communication in later slides when I discuss skew tolerance in our project. MPI-2 and OpenMPI contained KNAM support. And CMA entered the stage in 2014. While LiMIC2 and KNAM are implemented as kernel modules, CMA is an in-kernel implementation. That is, it is incorporated in the mainline source trees of the Linux kernel. It also has new system calls to invoke the features provided by CMA. The current implementation of MPI-2 uses CMA as default intra-node point-to-point communication channel for large messages. As far as I know, MPI-2 and OpenMPI also support CMA. XPMM is the youngest implementation of kernel-level support. The implementations I mentioned so far map a buffer of another process into the kernel address space. Unlike these previous implementations, XPMM maps the remote buffer into the user address space. This can provide zero copy data access. As Professor Panda mentioned yesterday, MPI-2 exploits XPMM for collectives such as reduction and data types. Few related publications from the MPI team are listed in this slide. So it has been 15 years since LiMIC was presented in ICPP 2005. Literally speaking, this research area entered the adolescent period. Hall described the adolescence as a time of storm and stress, and we know this as we all went through this period a long time ago, and my kids are in this period now. Anyway, as adolescents face tough challenges, I think that kernel-level support also needs to address challenging issues for large-scale systems, such as power efficiency, skew tolerance, and better manageability. These issues are not something new, but have not been thoroughly studied in terms of intra-node communication. So we'd like to answer about these issues in the Post-LiMIC2 project. Our project is a small part of a large research project funded by Korean government. The title of the entire project is Development on Computing Nodes of Supercomputer based on Super Parallel Processor, which will be led by ETRI. Yes, I know the title is not fancy, but this is what we decided. Two national institutes, ETRI and KISTI, more than 10 universities, and several companies are participating in this project. This project comprises 4 divisions. KISTI is the leader of the second division, which is responsible for development of supercomputing software stack. The Post-LiMIC2 project locates in this second division. From the next slide, I will share our research plan to address 3 issues I just mentioned in the previous slide. At first, I like to describe how we are gonna address the power issue. As we know, when an MPI application calls a blocking API, the MPI library internally pulls the state of the request until it is completed, and then returns to the application if the request is completed. The blocking APIs include MPI send, MPI receive, and MPI wait. This polling-based blocking provides good performance with respect to latency. This design assumes that an MPI process occupies a CPU core exclusively. However, it burns CPU resources. More importantly, it can waste energy if it takes some time to finish the application's request. To resolve this issue and save energy, we are implementing event-based blocking for intra-node communication. We can implement event-based blocking by using either signals or semaphores. We can block a MPI process with sig-stop signal and resume it with sig-cont signal as shown in the upper figure. This figure shows the eager protocol case. However, signal can be lost if the corresponding process is not ready to receive a signal or the process has multiple pending signals. Therefore, we are implementing event-based blocking by using semaphores. We can block and wake up an MPI process by calling sempost and semwait respectively. The bottom figure itself is more or less the same with the signal case, except that it uses a semaphore. Let me show you some preliminary measurement results of event-based blocking. We measured the energy consumption with a modified OSU latency microbenchmark. We added artificial skew represented as n microsecond in this pseudocode so that we can observe the impact of different blocking duration on energy consumption. As expected, event-based blocking saves more energy compared with polling-based blocking. We can see that the benefit of event-based blocking increases as the blocking duration increases. These are somewhat obvious. However, event-based blocking adds overhead to schedule a process. It doesn't come for free. To analyze the dark side of event-based blocking, we measure the latency without artificial skew. Since this experimental system is not a high-end node, we are not interested in absolute numbers of latency in this graph. As we can see, event-based blocking shows higher latency compared with polling-based blocking. So there is a trade-off between energy efficiency and latency. We are thinking that choice between polling-based blocking and event-based blocking is highly depends on the characteristics of the target application and the system where the application runs. As ongoing work, we are implementing event-based blocking for blocking APIs over Rendezvous protocol. Once we support all blocking APIs, we will move to support for non-blocking APIs. We are also interested in running our event-based blocking with MPI EA once our implementation is ready. Now let me move on to the issue of skew tolerance. Skew has been pointed out as one of causes that degrade applications' performance on large-scale systems because it results in high synchronization overhead and waste of resources. The skew happens due to network latency, uneven workloads, and etc. The blue bars of these figures represent different execution time of MPI processes, which are also started at different time points. Consequently, in the upper figure, the root node that calls a collective should wait until all other processes arrive to the collective. This problem can be resolved by making processes continue its next missions without waiting for other processes. One way to implement this idea is to provide asynchronous communication. The bottom figure shows that the root process returns asynchronously as other processes do not arrive yet and performs its computation work. In this way, asynchronous communication allows the overlap between communication and computation and can mitigate the side effect of skew. It is required that the synchronous semantics of existing APIs should be still preserved, though it returns asynchronously. Please note that here I'm not talking about non-blocking collectives in MPI-3. There have been few studies for asynchronous communication in terms of MPI Intra-Node communication. However, these studies have not yet addressed the collective specifically. Although some of researchers showed collective numbers, it is based on the asynchronous point-to-point communication. So in our project, we are trying to implement collective-aware asynchronous communication. To support asynchronous return while preserving synchronous semantics, we use page protection. So if a process touches the communication buffer for which communication is not completed, a page fault arises. If this is the case, we do rollback and perform synchronous communication. To overlap between data movement and computation, we offload data copy operations to copy engine, such as Intel IO80. The copy engine is a DMA engine that can move data between buffers without interference on CPUs. We implemented per-core request queues and callback function to efficiently manage the copy engines. As I mentioned earlier, if applications touch their buffers before completion, our asynchronous collectives do rollback and perform the rest of communication synchronously. In synchronous communication, CPUs take care of data movements. Even in this case, we try to maximize the parallelism between data movements by deploying the improvements we described in MOG 19. Let me briefly describe the basic ideas of these improvements. MPI Bcast with LiMIC2 initially had a limitation that the memory mapping operations on different processes was sequentialized. To eliminate this problem, now only the root process performs the memory mapping operation once. In case of MPI gather with LiMIC2, data copy operations were sequentialized because only the root process performed copy operations. In enhanced implementation, each process performs a copy operations so that it can overlap with others' copy operations. Let me summarize our asynchronous collectives with this figure. The blue lines represent the asynchronous return. When an MPI collective API is called, LiMIC2 inserts request to the intermediate queue, and the MPI library returns asynchronously to the application. The green lines represent the interaction with copy engine. The callback function is invoked whenever the copy engine completes a request. The callback function determines whose requests to handle and how many requests in per-core queues to handle. The red lines show how the rollback works. The communication buffers are protected as soon as a collective API is called. When an application tries to touch the buffer, can I use the mouse? Okay. Do you see the mouse here?
Yes.
Oh, okay, great. The communication, where is the mouse? Okay. The communication buffer is protected as soon as the collective calls is invoked. When an application tries to touch the buffer, the signal handler is invoked. This signal handler requests the rollback to LiMIC2. Then the corresponding per-core queue is disabled. And the data is moved by CPUs instead. This slide shows some of the preliminary measurement results. As we can see, we could improve the latency of MPI broadcast and MPI gather up to 28% and 93% respectively. However, we can also observe that there are significant overheads with asynchronous communication for smaller messages. on this left side figure. This is mainly due to the initialization overhead of page protection. We also measure the performance of synthesized applications. Although I'm showing the pseudocode in this slide, frankly, what they do is neither realistic nor meaningful. I just show these to say that the purpose of these experiments is to see how well MPI bcast overlaps with matrix summation or matrix multiplication. Oops. As we can see in these graphs, our asynchronous communication well overlaps with computation. The reason why we don't see much difference with the matrix multiplication is that the computation time for multiplication is too high compared with the communication overhead. Thus, the benefit of overlapping isn't shown on much. As ongoing work, we are implementing several policies in the IOAT callback function. We plan to support other collectives than MPI bcast and MPI gather. In addition, we are looking for applications that can benefit from asynchronous collectives. Actually, we initially considered blocking collectives only, but since the concept of asynchronous collectives is very close to non-blocking collectives in MPI 3, we are recently considering these two. Now let's take a look at the manageability issue. As I have explained in beginning of kernel-level support for MPI Intra-Node communications, since these implementations have different advantages, hybrid approach might be a good choice to optimize the performance of intra-node communication. For example, MPI-2 uses CMA for point-to-point communication and XPMM for some of collectives. However, it will be cumbersome to manage several kernel modules or kernel patches in a large-scale system. Before going into discussion for our approach, let me show you some measurement results to compare kernel-level mapping and user-level mapping. As I have mentioned, most implementations of kernel-level support, such as LiMIC2, KNAM, and CMA, provide kernel-level mapping, but XPMM provides user-level mapping. This slide shows the performance with the map and copy workload, which is very close to the traditional communication pattern. As we can see, LiMIC2 kernel-level mapping shows significantly better performance than XPMM, which is a user-level mapping. This is mainly because memory mapping and page fault overheads of user-level mapping are high. However, in the map and read workload, user-level mapping shows significantly better performance than kernel-level mapping. I borrowed these graphs from this IPDPS paper of NowLab. This better performance is mainly due to zero copy access provided by user-level mapping. Since both kernel-level mapping and user-level mapping have their own advantages, we are trying to support both kernel and user-level mapping in a single kernel module. To do this, we added new APIs into LiMIC2, such as LiMIC-X, RxComp, and LiMIC-X, RxComp no cache. In addition, we implemented a cache for user-level mapping because user-level mapping has higher mapping overheads. This idea of having a cache is borrowed from MPI-2, and we thank Jahanjip for his suggestion regarding this cache implementation. The difference from MPI-2 plus XPMM is that the cache is now in the kernel module, and the MPI library can utilize the cache transparently. The cache is implemented with a red-black tree and uses RRU policy for eviction. This slide shows our preliminary measurement results with the map and copy workload. In these graphs, one of y-axis represents the performance of kernel-level mapping. As you can see in the upper graph, user level mapping shows comparable performance with kernel level mapping, even in map and copy pattern with 100% cache hit ratio. But when the cache hit ratio is low, its performance becomes worse. There is no surprise. The intention of these experiments is to show that our implementation of user-level mapping has a decent performance and works well, rather than who wins and who loses. As ongoing work, we are stabilizing the implementation. In addition, we need to see whether the patch for MPI-2 will be valuable. Also, if this is the right way for better manageability, and we really decide to combine these features in a single kernel module, we will need to carefully see if there is a license issue. But we haven't gone over this issue yet. In conclude, we just started Post-LiMIC2 project, and we will cover the issues such as power efficiency, skew tolerance, and better manageability. We will be happy to discuss with you people regarding all these issues. There are also other research topics in our project, but I couldn't cover all of them in this talk. Maybe next time. And we hope that we can collaborate more closely with the MPI team for finding new features required to kernel level support and efficient ways of using kernel level support in the MPI level. Thank you for giving an opportunity to introduce our project in March 2020. Thank you.
Thank you, Jen. We really appreciate your talk. There is a question on chat. So
okay.
Yes. How much is the user to kernel context switch overhead in this implementation?
For which one? I mentioned the 3 topics. So is the question specified one of these 3 things?
Unfortunately, no. Devesh, can you follow up? Can you clarify?
Oh, maybe if he or she mentioned the context switch, I think he was saying about the blocking thing.
Yeah, I think the user just followed up. It's like signal based. He mentioned signal based.
These results are shown showing with the semaphore based. So in this graph, can I change the pointer? Oh, great. In this graph, we can see a higher overhead with the event-based one. So this can be a context switch overhead.
Okay.
But we didn't go over the detailed overhead analysis yet.
Okay. Thank you. So I had a follow-up question. So one of the issues that we faced with the XPMM implementation was the problem that any buffer registered with XPMM could not be registered with the InfiniBand driver. So have you guys tried to address that issue?
Last year, Professor Panda mentioned about that issue, and we took a look at the source code. And that time, currently we are not sure whether we can have we can come up with a solution to resolve that problem. But we figured out the reason of that issue. But currently we are not sure whether we can resolve that one or not, because it's related with some protection issue. So we are not sure whether we can violate that protection or not. So we need to first check that thing, then we can come up with some solution. Okay. Maybe we can discuss more about that after the mock.
Sure, thank you. So thanks a lot for your great talk.
So Hari, one sec, please. So hi, Dr. Jin. This is Jahanzeb. Very nice talk. Yeah, nice to meet you again.
Great.
So yeah, really a lot of improvements have been done. I really appreciate that. So I had few questions that I was having. So the first one is that now that you have this in this hybrid LiMIC plus XPMM where you have the cache in the module itself, right?
Right.
So have you tried to do some instrumentation of how much of a system call overhead will that be for each of the IOCTL calls that you'll be making? Previously, since the cache was in the user space and the map, once the mapping were created, there was no context switch at all, right?
Right, right. So currently, the reason why we put this cache thing to the kernel module is to provide some kind of abstraction to the upper layer. So we need to analyze the performance as well, so that whether this design is reasonable thing or not. But we haven't gone for the detailed overhead analysis yet. So this is just a prototype implementation. So we need more analysis about the system core overhead, those things.
Okay, sounds good. Yeah, we can sync up later on as well.
Yeah, right, definitely.
Thank you.